let me just recap yesterday's lecture, right? We introduced vectors, which have these properties. They're arrows, essentially, with both a magnitude and a direction. I claim that there's a good reason to be looking at them. We spent most of last class looking at operations with these arrows, right? We could figure out how to add them together. We could subtract them. I mean, once the subtraction comes basically once you figure out how to add them and how to multiply them by numbers. And we introduced a couple of, I claim, were special arrows, right? Ones that were of unit length and just gave you a direction in essence. And then we did two examples, right? One example was how these arrows, how these vectors come up in force diagrams. If you remember physics, oftentimes if you're supposed to analyze a static setup of the forces acting on some idealized particle, then you have to add these arrows together. And we saw that this was essentially just vector addition. And then there was a more geometric problem, which was finding a direction of a tangent line. So if I have a curve in 2 dimensions, there's a notion of at each point from one variable calculus, we know that we could take the derivative, and the derivative is a slope of the tangent line at each point. And it turns out that I could rephrase this or reframe this problem in terms of taking, if I have a line and I know the slope of a line, then in fact I could tell you direction vectors. I could tell you which direction the line is pointing just by reformulating this problem in terms of a vector. So at each point of a line, given its slope, I really could just enter the slope in the y component of my vector if I'm in 2 dimensions, and input 1 or minus both in the x component, and that gets me a direction vector. All right. Now there are two sort of possibilities I want to go from here. The first one is at this point we could see how, given a line, we're able to find a vector associated with a line. And so this poses a question of maybe if I have a vector, if I have a direction that I want to go in, that really should be sufficient to tell me what the line is. In other words, instead of looking at the usual line equation, y equals mx plus b, which is a line in 2 dimensions, I should be able to use this framework and flip it on its head and say, if I have a direction vector and also a point I want the line to go through, that should be sufficient to tell me what the line is, right? In this case, I have a blue point here, and I have a direction vector, 1m, let's say this way. Then, if this were just a piece of paper, right, and I gave you a dot and an arrow here, you should be able to draw me the unique line that is this. So how do I reformulate this in a more mathematical setup? So that's the first point. The second point is then, if I could do such a thing, if I draw any other line here, if there's a line 2 that goes this way, that might form that intersects at this point, and it'll form an angle with my red line here. And in a sense, all the action is happening at this point here, right? There's a point here where the intersection is happening, and there are 2 arrows. One arrow with 1m associated to my direction vector for L, and then there's another arrow associated with a direction vector for my intersecting line. And those 2 vectors at this point entirely capture the geometric situation near this point. And so if I want to find the angle of intersection, there should be an easy way, or I hope there's an easy way to read off this information just by vectors, just by looking at what the vectors are. So that's the second point we're going to look at today's class. The first one is how we are actually going to get lines from vectors, direction vectors. The second point being how we might find ways to calculate angles between vectors. All right, and the latter point is going to involve a type of calculation called a dot product and also a cross product in 3 dimensions. These are ways of multiplying vectors together. Okay, so a lot of talking. Let's get at it. So those are the motivations. And so the first thing here is, how do we get? So last time we saw in 2 dimensions, we saw that a line y equals mx plus b has direction vector 1m, or in essence, any scalar multiple of this, right? If I just scale this by any number here, that's lengthening or shortening or reversing my vector as long as it's not zero. And that still gives me a valid direction. It's just in essence how fast I'm going, but it doesn't change the direction at all. So now, is there a way to reverse this? So the question here is, given a point P equals x and y in coordinates, maybe I'll say x naught, y naught, and direction v with, let's say, vectors a, b, can I describe a line? So let's take a look at this. Let me draw a crude diagram here. So here's x, here's y. Here's a point that I want. It has coordinates x naught, y naught. And I have a direction v that I want to go in. And in component form, this has components a, b, right? To be clear, this does not mean that this tip here has coordinates a and b. Remember, this just means that if I have an imaginary little different Cartesian plane, adapted to this vector here, and I put x and y here, then this has length a, this has length b, right? That's roughly what this means. Now I can modify this a little bit and consider the vector, because I'm living in R2, the plane. I could make a kind of stupid adjustment here, right? At first, P is given the coordinates x naught, y naught, but there's nothing really stopping me from just associating a vector to P. All right, I'm going to associate a vector to P that has tail literally at the origin in my xy coordinates, and the tip is going to be at my point P. So this I'm going to call R0. So R0 is the position vector of P. So it has components x naught, y naught. Exactly the coordinates of my point P is called the position vector in the plane. And now I could do something, which is I could just add these two together, right? I have a resulting arrow. If I add R naught to V, I have an arrow that points from the tail of the red to the tip of the green. And this is R0 plus V. Now, if I look at the coordinate here, is R naught plus V, the tip of this arrow, is it going to be on the line or off the line? Right. So this certainly is on the line. Now, what if I modify this setup even more? So what if I go, instead of this, I also look at, I could scale V, right? There's nothing stopping me from, say, going, extending V a bit. So if I have V here, then the dotted, if I continue it here, this would be 2V, right? If I, this is some length, I could scale it by 2, pointing in the same direction. This is 2V. And I have a resulting arrow here, which is formed by R naught plus 2V. Now, is this on the line or off the line? Right. So it looks like I could scale this by any number I want. This is 1V, 2V, 3V, so forth. And every single point on this line, in this direction so far at least, is given to me by R naught, which is x naught, y naught in component form, which in essence is just P. That you could, I just change the brackets just to make the types match up, right? X naught, y naught was a point. Now I want to make it, quote unquote, into a vector. So I put angle brackets around it, and now I can add vectors. And I just keep adding multiples of V in this direction to get a line this way. And I could also do it the same way here, right? So I could reverse this, right? This is minus V. And I could also have a point here that is R naught minus V. And this point is also on the line. It's just going backwards. So you could see that I could just scale V by whatever I want. And together, that's going to trace out my line L. So what does this mean? This means I get a parametrization of my line. We get a parametrization of the line. We can describe the line L containing P with direction vector V by the following. R of T is going to be the position at time T is equal to R0 plus T times V, where T is a real number. Or I guess I could do T ranges from the entire, on the entire real line. So this is like the position at time T, right? And you'll notice at T equals 0, this disappears here at R0. So you're at P. At time 1, you're here. Time 2, you're here. So forth. At time minus 1, you're here. So forth. This is I think the way that your textbook presents it. I prefer parameterization. We know about parameterizations. So this in essence tells you, in other words, L is parameterized as x of T is equal to your starting x naught plus T times the x component of your direction vector. and then y of t is equal to y naught plus t times b. Now, what's nice about this is it generalizes. This generalizes to 3 dimensions and higher. What do I mean? It means that given a point P with coordinates x naught, y naught, z naught, and direction vector, and vector A, let's say V is equal to angle brackets A, B, C, the line L passing through P at time equals 0 in the direction V is the following: x naught plus TA, y naught plus TB. And what's z in this case? So we've done this in 2 dimensions. In 3 dimensions, we have another z component. And in this setup, what should it be? It should be z naught plus TC. That's correct. So, okay. Question in chat. This has Ibrahim asked, this gives the tangent line as a vector. In the previous case, yes, right. If you looked at, we used to have a curve here. I said L was a tangent line, and now I'm describing that tangent line as a parametrized curve, as a parametrization, right? But this, forget about tangent lines at all now. Now I'm saying if I just have a point and a vector, given the information of a point and a vector, I know I can now tell you exactly how to describe the line going through that point at time equals 0 and traveling in the direction of that vector. Okay, forget this line doesn't have to be tangent to anything. It's just any line now. I'm just looking for lines, how to describe lines given a point and a vector. All right, and this is how you do it. So this is parametrization of lines. So okay, so let me address some questions. It's a lot to take in the first time, I understand. So R0 is just a formality. Okay, what I have here, this is something your textbook does. A lot of textbooks do it to introduce it, but in essence, people don't really use this other than to make things make things correct. But the point is, R0 is the position vector of the point P. All right. For all intents and purposes, P itself is R0. I just renamed things. All right. So it's like typecasting in computer science or something, right? I've coded something up. Originally, I had a pair of numbers, x0, y0. They gave me the coordinates of the point. All of a sudden, I'm going to change the type of this point into vectors. The point being that I am allowed to add vectors together, right? So if I just make this point, I take the point with coordinates x0, y0, and just make it a vector with components x0 and y0. I'm going to interpret this vector as the one with the tail at the origin in my coordinate system, and the tip of the arrow is going to be at my point P of x0, y0. That's what R0 is. It's just my point P, but I'm representing it in kind of a stupid way. I'm saying, let's just pretend it's a vector now for whatever reason. And the reason is because it's a vector, from what we learned last class, we could add vectors together, right? In 2 dimensions, really, we can't add points together. It doesn't really make sense for me to have a point here and a point here and add it together. If you're adding them together component-wise, what you're doing is you're interpreting it as a position vector here and a position vector here, and you're adding up position vectors to get a new position. But that technically uses the fact that you can represent these points as vectors in Euclidean space. All right, this is not at all a general thing, right? If you think of a general surface, let's say you're on the surface of a sphere, okay? Then I can describe a point. First of all, you run into trouble. How do you describe a point on a sphere? You have various coordinate systems you use, latitude, longitude, or something other than that. You can represent any point you want, depending on your coordinate system. Then 2 points on the sphere, which is like a spherical shape. What does it even mean to add these 2 points together? You really can't. You have to figure out how to add something like a position vector, but even then you can't really add the position vectors on the sphere because your sphere is not a linear space. This is getting into the weeds here, but in general, you need to rely on the fact that in R2, everything works out such that points you can typecast successfully, or just change types from a point into vectors and then add up the resulting position vectors and add together points. That's all R0 is here. All right, it's really not that important. There's nothing deep going on here. I'm just making sure everything's correct so that we can actually add vectors like adding vectors is a valid operation. Okay, so I turned P into a vector and I added it to form this line. All right, let's do an example. And this is pretty formulaic. So I think one example for now should suffice. So let's find a parameterization of a line L in R3 passing through let's say the point 1, 2, 1, passing through the point P, 1, 2, 1 with direction vector 2, 0, or 2, minus 1, minus 3, such that, let's say part A of this, L passes through P at time equals 0, and B, L passes through the point P at time equals minus pi. Let me scroll up a bit so you could actually see the formulas again. So I'll give you a couple minutes to think through this. In particular, part B, right? Part B is, I didn't really tell you exactly how to do this one, but I'm hoping, let's see if you could think your way through how you might get part B from part A. It's perhaps helpful to have in your picture a diagram like this, right? The diagram in R3 is exactly the same as the one in R2. It's just you have, these are three-dimensional vectors. It's just harder to draw. So for A, we have the following. This is basically the highlighted bit in green, right? You could just plug it in and it's just a machine that gives you the parametrization, right? So the points of P, X naught, Y naught, Z naught are 1, 2, 1. It's pointed out in chat. So we plug that in, right? It's 1, 2, 1. That's your X naught, Y naught, Z naught. And then you have direction vectors, right? So direction vector is A is 2 in the X component. So there's 2t plus or minus 1 times t. So that's minus t. And then we have minus 3t. So there you go. Now, does someone see a modification of this to get me part B? Wow, interesting. Okay, so Ibrahim has a okay, so we have several ideas. Ibrahim says we could just plug a translation in T, basically. That's perhaps the most straightforward way. Rafal says sine of T instead of T. Yeah, I mean, so the issue with sine of T, that's actually very creative. I like that a lot. Okay, so the issue with sine of T is certainly it does. So in case, to explain to everyone who maybe don't see it immediately, well, sine of T happens to the it just so happens completely coincidentally the sine of minus pi, right, is sine of minus pi is 0. So if I just replace t here with sine of t, then certainly a sine of t at t equals minus pi, this will be sine of minus pi, so this is 0. So I'll get 1. This is also 0, so this is 2, and then 1. So I'll certainly start there. Now the issue is if I want the entire line, right, the line has to span from, the line has to be never ending, right? It needs to be, it's not a line segment, but it's rather, it's infinite in both ends in a sense. So what sine of t would get me in this particular parameterization is, I could, if I don't restrict t, if I let t be the entire real line, then sine of t oscillates between -1 and 1, right? So what's going to happen is I have a point. I'm going to draw schematically here. Let's say this is my point 1, 2, 1. At t equals minus pi, I'm at this point, and then I have some direction that I'm going into. As sine of t increases, I'm starting to shoot off in this direction, whatever that is. I'm just going to schematically draw it. Maybe this is V. And then what's going to happen is I'm going to have a point that starts here, and then I'm going to go here, here, here until sine of t reaches its maximum, let's say 1. And then I reach exactly 2 minus 1 minus 3 away, and then I start reversing again because sine of t is going to decrease, and I'm going to go over here, and then I'm going to oscillate back and forth from here. If I allow t to go from minus infinity to infinity, and this is just sine of t, then I'm going to actually oscillate in a bounded line segment. I'm going to go back and forth from this point here. All right, so that's the answer to Rafal's idea. It's fascinating. I actually didn't think of that. Very creative, but not quite what we want. But so to oscillate back and forth on this line segment, you could put sine of t, and it does satisfy the requirement that at t minus pi, it does pass through this point, and it also has the correct direction vector. The issue is it's not exactly the entire line, so that's not entirely correct. But that's very creative. Part B, the easiest way is to translate this. You could do the following. I'm going to have the same starting point here, 1, 2, 1. And then instead of t, I could just subtract off, right? Or I guess add t plus pi to everything. And what's happening here is, I hope algebraically it's somewhat clear, right? If I just replace t, this is kind of like a change of variable, right? I'm like replacing t with, like, let's call it u everywhere, where u is equal to t plus pi, and I'm just writing it out. And it has this change of variable has a property that, at t is equal to minus pi, well, this vanishes, right? At t equals minus pi, everything's, this vanishes, and I'm at 1, 2, 1. So this does satisfy it. And if you really want to clean this up a bit, then you just multiply everything out. So this becomes 1 plus 2 pi plus 2t, 2 plus pi minus t, and then you have 1, oh, sorry, not 2 plus pi, that's 2 minus pi minus t. And then you have 1 minus pi minus 3t, right? This is I'm just collecting the constants here and then a t parameter here. Any questions on this method? Is it minus 3? Yeah, it is minus 3 pi. Thanks, guys. So that's the quickest way. I should probably, it's important to include your parameterizations. These all have t's ranging between the entire, on the entire real line. So there you are, an example of how to parameterize lines in 3-dimensional space, or 2-dimensional space, or 500-dimensional space. Is all the same. And it really just comes from vector addition. We'll revisit some more properties of lines later, but let me go to the other motivating example. Let's consider the following, right? Consider the moral first is, given P and direction V, we can find L and vice versa. So these are equivalent pieces of information. So the question now is, if L1 and L2 intersect at the point P, so if I have another line, let's say I have another line this way, and it intersect at the point P with direction vectors V1 and V2 respectively, can we find the angle of intersection? I should probably say acute. I mean, the angle, it's there are multiple angles, right? You could take the obtuse angle or the acute angle of intersection, but I'd specify this in an actual question. The question being, if I have L1 and L2 now, they intersect here, and they have two vectors here and here. Can I find the opening here? And theoretically, because of how the angle, I want the angle of intersection between these two lines, but the line information, as we just saw, is exactly the same thing as giving a point and a direction. So is there a way, basically, given two vectors at a point P, can I find the angle between them? Okay, so that's sort of the motivation that I have now for our next operation. All right, so let me just introduce the dot product. So this is a new operation. The dot product is the following. So given two vectors, let's call it V1 has A1, B1, C1 components, and V2 has A2, B2, C2 components. The dot product is a way of multiplying them together. All right, so the dot product is the operation given by, the notation is there's a dot in between them. That's what's called a dot product. And what you do is you multiply each of these components together. So the x components gets multiplied together first. So A1, A2, and then you add that to the second component getting multiplied together, B1, B2. And then the third component, in this case, C1, C2. So note that this operation takes in two vectors, and what comes out of this? Is this a vector or a number? Right, so this is a number or a scalar, okay? So this takes, so this is like a machine, all right? So if you're coding this thing up, you maybe write some sort of function for this. It takes as input, it takes in vectors, and it outputs a number, or I guess I'll call it a scalar. So it takes in vectors and outputs a scalar. And furthermore, so this works in any dimension as long as V1, V2 are the same dimension. By dimension, I just mean how many components they have. All right, so in this case, I've given you 3-dimensional vectors that have 3 components, and you just max them up component-wise and pair them up like this and add it together. Okay, so you can see if these are 500-dimensional vectors, you would have 500 of these pairs, right? So long as each of these get mapped together. So very arbitrary so far, but let's see what properties it has. An important property is, this is not at all clear, all right? And you could actually show, I believe if you're curious, you could look in the textbook, it shows you how to prove this. But in essence, this is like the law of cosines. So remember, if you think back to high school or pre-calc, or whichever that part in like trig that no one pays attention to, right? There's like a usual Pythagoras and like all that stuff, and there's like the law of cosines, and everyone just forgets it and you look it up, right? But that's how you prove this following result. The property is V1 and V2, the dot product of it is the same thing as the magnitude of V1 times the magnitude of V2 times cosine of the angle between them, where theta is taken between 0 and pi. What's the diagram of this? It's telling you that if I have two vectors, so again, vector 1, V1, vector 2, V2, right? Let's draw an imaginary line along the direction of V1. Then, there are many ways V2 could be oriented, right? So this way, whatever. But there's an angle between 0 and pi that I could draw from here to the opening of V2. In this case, it's this opening here. That's theta. If V2 happened to be pointing this way, then I'd be drawing the angle this way, right? Just for theta to be between 0 and pi. All right. So there's a following relation here, and you prove it using some awful trick. But in other words, what this tells you is, so this is equivalently the cosine of the angle between them. If you take the angle to be between 0 and pi, if you express the angle between them between 0 and pi, then cosine of the angle between them is precisely given to you by the dot product divided by the usual product of their magnitudes, right? Remember, the magnitudes are just numbers, so you certainly can multiply two numbers together, and you could perform this division. All right, any questions? Oh, right, sorry, theta can be pi. I'm sorry, yeah, to be less than or equal to. Okay, so reading off of this, so that's the first property. We'll do an exercise on this very soon, and then there are just algebraic properties. Let's say you have symmetry. V1 dotted with V2 is the same thing as V2 dotted V1. This looks like a stupid thing to say, right? I mean, it's something you would expect for numbers. I point this out because we're pretty soon going to introduce a different type of vector product for which this is definitely not true. All right, so in this case, the dot product is very nice because a lot of the things that you expect of a dot product, it is certainly true. So this is symmetry. And then you have the fact that if you have a vector W dotted with the sum of two vectors, well, it distributes, all right? So just like if you just pretended these were numbers, right? Then you would expect some number multiply the sum of two numbers, you could just distribute it across over the brackets. Well, this also satisfies it. So it distributes. And also you have something called associativity, all right? So you have the fact that if you do, this is pretty dry, so more in textbook. All right, so the rest you could find in the textbook. There's just a bunch of algebraic rules that these things satisfy. All right, so this stuff is a whole lot less interesting than this property here, which is really what we care about, the dot product. So let's do an example with this. Let V1 be the following vector. Let's say it's what is a vector? So let's say find a vector V2 such that V1 dotted V2 is equal to 0. What angle is between V1 and V2? All right, so here's your formula for the dot product. This is a two-dimensional vector, by the way, so your formula simplifies somehow. I'll give you a few moments to think about this, and maybe you could write your ideas down in chat. Maybe I should specify this just because some of you are sneaky. This is find a non-zero vector V2 such that this is true. Okay, so I'll give you a minute to think about this. Okay, so do we have ideas on what this is? Okay, negative reciprocal, and it will be orthogonal. So yeah, let's discuss this. So there are multiple ways, right? So we want, let's say V2 is equal to AB. All right, so we need V1 dotted V2 to be equal to 0. And what does this mean? Well, this means that 1 minus 3 dotted AB must be equal to 0. So this means that if I expand this out, you have 1 times A plus minus 3 times B. So you want A minus 3B must be equal to 0. All right, so you need the components, in other words, to satisfy A must be equal to 3B. And so you get a family of bunch of vectors, right? So everyone says, let's look at chat. So Ibrahim says A equals 3 for all B and R. Yeah, that's correct. Well, except for 0, right? You can't have 0, 0. So we're disallowing that. But I just really wanted to find a vector. So you could plug in anything. So to get a vector V2, set, let's say B to be anything in R, to be anything non-zero. For example, B equals 1. And then so A, in this case, would be equal to V3, right? So then V2 is equal to 3. 1 is an acceptable choice. And now you could read off of what this means. Well, it means that this is orthogonal to V1. All right, remember, this tells you that the angle between vectors, roughly speaking, the dot product of it, if you ignore their magnitudes, these are non-zero. These each are non-zero. So it means that if the dot product is zero, then cosine of theta has to be zero. So where is cosine of theta equal to zero? Well, it has to be equal, well, zero at pi over 2, right? Especially on this interval here is equal, when theta is pi over 2, cosine of theta is 0. So when the dot product of two non-zero vectors vanish, that means that their angles, the angle that they form is 90 degrees. Right, so we have this example here that, well, it's an example in 2 dimensions here that tell you that whenever vectors are, if the dot product of non-vanishing vectors, if they're 0, then it must be the case that they're orthogonal to each other. So that's the dot product really is a test of orthogonality, whether or not you form 90 degrees. Okay, and this example here doesn't really, well, this is a 2-dimensional example, but this property of dot products works in any dimension, all right? Basically, what happens in 3 dimensions, if these were 3-dimensional vectors, well, if I take 2 vectors by 2 arrows in 3 dimensions, then visually you could confine these arrows to a plane, right, to a 2-dimensional surface, and then the angle would just be with respect to that 2-dimensional surface. In other words, right, if I give you two arrows in 3D, then you could put a piece of paper to it such that the arrows are lying flat on the sheet of paper. You could draw an angle between those arrows, and that angle is going to be this angle theta, and everything here still holds, all right, in 3 dimensions. So let's do an example. Let's say find the acute angle theta between the vectors v1 is equal to 1 root 2 minus 1, and v2 is equal to 1/2 1 over root 2. So as you work through this, let me recall, because I can't scroll up anymore. 1 out v2 satisfies the following. Maybe I'll write this out. So this is 1 times 1/2 plus root 2 times 1/2 plus, or minus 1 times root 2 is equal to 1/2. Now, what are the magnitudes of v1 and v2 respectively? So I need v1, v2. All right, so this should be, well, let me just do the first one. I'll write it out. This is 1 squared plus root 2 squared plus 1 squared again is root 4, so it's 2. And then I have 1. All right, so what does this formula tell me? It tells me that the cosine of theta must be equal to this divided by that. All right, so this is 1/2. And the other thing here is going to be, well, it looks like 2, which is 1/4, which is not the nice number I wanted. So I screwed up in making this problem. Oh, well. Okay, so theta is going to be arc cos theta, or arc cos of 1/4, where theta is between, you have, so, this is not something that you could calculate by hand. So you plug it in your calculator and choose the theta that's in between 0 and pi over 2, because I want the acute angle. Okay, with this, let's now have let's now sort of apply this to one of our problems earlier, which is finding the intersection angle between lines. Suppose L1 and L2 are lines in R2 with equations y is equal to m1x plus b1 and y equals m2x plus b2, respectively. Suppose L1 and L2 intersect at a point P. What is their angle of intersection? And for their angle, I'm going to allow, you could, for any crossing, right, it's going to be an X. You could measure the angle in 2 different ways, right? It could be the obtuse angle or the acute angle, and I'll leave that up to you. So it doesn't really matter, either obtuse or acute. So how might I go about this? I have the standard line equations here, and preferably I want to use something, I have a toolbox now that operates on vectors. I do have non-parameterized lines in R2. So somehow I need to get the expression from, I use the expressions of non-parameterized lines in R2, and I need to get some expression that gets me the direction vectors, and maybe I could do something with direction vectors. So the first step is, what are the vectors that I need associated with L1 and L2? So what are the direction vectors So L1 has direction 1, M1, right? Because this is a slope. So this is just like at the end of last class, right? Where we had the equation of a tangent line with a given slope. It was a derivative at that point. And now we could turn the slope information to a direction vector just by inputting 1, and then y must change by the allocated ratio given to you by your slope. So this is 1, M1, and L2 has something similar. It's given to you by 1, M2. And now what should I do with these two direction vectors? What's the dot product of these direction vectors, first of all? The dot product of them would be, be 1 plus M1, M2. And the magnitudes are going to be equal to 1 plus M1 squared, square rooted, V2. So 1 plus M2 squared, square rooted. And so I have the fact that cosine of theta, well, it must be equal to the dot product over root M1 squared plus root M2 squared. And so theta is going to be arc cosine of 1 plus M1 M2 over these quantities here. So once again, pictures, it's L1, it's L2, some point P here. I found vectors, say V1, say V2. Maybe I found V2 here. Then I found the angle between them. All right. There's an indeterminacy here, right? Depending on which way I point my slope, I could also go minus V2 here, and that's going to get me a acute angle. So at least one of the angles are going to be found by this. And if you want either you're fine with the obtuse one, or if you want the acute one in this case, you'll realize that this solution might be given to you something greater than 90 degrees. So then you would just take 180 minus that to get this acute angle between them, if a question specifies. All right, but in general, this is what the formula is. Okay, Sophia asks, how did I get the direction vectors in the first part? This is it follows from the discussion last class, where I have a line given to you in point slope form, or whatever standard form, I forget what they call this, right? It's the one with the slope. You don't care about the intercepts. You just care about the slope of the line. And the slope tells you that when you go in x units in the x direction, you must go up in y by m1 times the x units, which means that if I go right and if I go in the x direction in 1 unit, I must go up m1 units to stay on the line, right? So in essence, the direction vector of the line must be multiples of 1 m1, right? I must always increment in that direction, in essence. So that's how I get these. Let's now take a look at a couple of useful other useful tricks that just come from this one starred property here. All right, so we've noticed that there's a way between any two non-zero vectors to calculate the angle, and something special also happens when one of these is a unit vector, right? Let's say v2 were a unit vector, then so that means something of unit length. Then that means that v1 dotted v2 is just the magnitude of v times cosine of the angle between them, right? So actually, since I drew this diagram here, it's probably easier to say v1 is a unit vector here. So let's say this is unit length, and then I have another vector v2, might be big, might be small, just whatever it is. This is just v2 times cosine theta, the angle between them. Now what this tells me is, if I now imagine these as forces, let's say v1 is pointing in some direction, and I care about the magnitude of the force in this direction. Then the magnitude of the force in this direction is the same thing as if I just make this direction have find the unit vector pointing in this direction, and then I just take the dot product of v2 against that. All right, so that's called taking the magnitude of this resultant dot product is called the component of v2 in the direction v1, and so that gets you in essence the magnitude of v2 in this direction. And if I actually want to convert that magnitude into an actual force pointing this direction, so looking at the actual force that v2 exerts in this direction, then I get the projection of v2 in the direction v1. Okay, I'll write this down shortly, but the purpose of this is, once again, in these force diagrams, right? If I recall, if I take your attention to last class, we had an example here, right, where we looked at the forces acting on this point. We used some trig with cosines and sines to figure out what the component of the forces were. But the other way to write this is if I cared about the component of F1 in the x direction, all I had to do was take the dot product of F1 with, if I had the expression of F1, then in component form, I just take the dot product of F1 with the vector 1, 0, and that gets me the component of F1 in the direction here. So let me write that down. So vector projections. So suppose v1 and v2 are non-zero vectors. The component of let's say of v2 in the direction of v1 is the following. So they call this component along v1. So v1 is a subscript here. v2 is large. This is given to you by the dot product v2 dotted with v1, the unit vector formed by v1. All right, and what is this? This is the same thing as v2, the magnitude of it, times cosine of the angle between v1 and v2. Diagram being, let's say v2, or sorry, v1 is this direction. It has a unit vector defining it, and then I have v2 here. Then I can project this downwards here, and there's going to be an angle formed between it and the magnitude of its projection, the shadow of this arrow in this direction, if you will, it is the component. That's the component of v2 and v1, right? So if you imagine shining a light here, there's going to be some shadow that this casts in this direction, if you will. If this were all confined to a sheet of paper and the sunlight was perpendicular, then there's going to be, some shadow in this direction here that v1 points in, and that's the component. Now the component could also be negative, right? If v2 were pointing this direction and v1's this direction here, then the component here, the dot product, would be negative. But that just means that it's roughly speaking, it's the same length, if you take absolute value, but it's just pointing in the wrong direction in a sense. Now there's a way to make this a vector, right? The projection of v2 in the direction v1 is the vector with magnitude given by this shadow, the component, in the direction given by the unit vector v1, v2, v1 over the magnitude v1. Actually, I should not say magnitude here because component, like I said, could be negative. Maybe I'll just do, the idea is you want whatever this shadow is. It's a number, but it might be negative. Maybe I'll say with coefficient. So what I mean is the projection is a vector and is given to you by the component times the unit vector v1, the unit vector in the direction of v1. Expand this whole thing out and you get something pretty nasty, but same thing as v2 dotted with v1 over the magnitude of v1, and then you got to multiply that by v1 over the magnitude of v1 again. All right, any questions with, conceptually with what the components and projections are? Right, so the component of a vector is always a scalar value, and the projection of some vector is always a vector. With roughly speaking, its quote unquote length of the projection is given to you by the component in that direction. Actually, now I think about it, I really hope I didn't screw up. These are not, your textbook uses this. I hope I didn't screw up the component projection. One of these is called, I hope it's not, projection being component and component being a projection, but these are the concepts. I'm pretty sure this is the order your textbook does it in. It's somewhat non-standard terms for these, but people use these concepts a lot. And one concept where this does come up a lot is, like I said, projections of forces. For example, if you have a point here, which is point A, and a point here, which is point B, let's say you move in a straight line path from point A to point B and you cover some distance or a displacement. And let's say your force, maybe this is a hill here, and you're dragging an object with this force here, always. It's constant, and you've moved it from here to here. So the physics of this would tell you care about the work done on this object. And the work done is actually force dotted the distance. All right, it's not really force times the distance. That's true in one dimension when you're forcing displacement are always in the same direction. But in this case, there's an angle that's made by the force and the actual distance along this slope that you've dragged the object. So what you really care about is the component of your force in this direction, the displacement vector from this to that. All right, there's a vector here, and you care about the component of force in that direction, roughly speaking. It's important to get a sense of what this quantity is, less so the actual name of what this is, but the idea of what components and projections are do come up in a lot of physical examples. So here we are. This is so that was a dot product, and I know I have a couple minutes left. Let me introduce the cross product, and next week we'll do more calculations with those, especially with in an application of what cross products actually get you. So let's recap, right? So far we've seen an operation that's completely new. That's not just addition and multiplication by numbers with vectors. So this is a dot product. It's sincerely just an operation on vectors. Right? We couldn't do this with numbers before. Well, we could just multiply the numbers together, but we didn't really have any generalization of that until now. And the dot product takes in two vectors and outputs a scalar. It works in any dimension. And importantly, it tells you something about the cosine of the angle between them. In essence, in any dimension, if the dot product is 0 between non-zero vectors, you get an angle. You know that these vectors are orthogonal. Now, oftentimes it's not enough to know whether vectors are orthogonal or not. Sometimes you want to actually construct an orthogonal vector to any pair. Now, this comes up a lot in 3 dimensions, right? Because we've done an example in 2 dimensions where if I give you a vector in 2 dimensions, I could tell you to algebraically solve for when the dot product is 0, and that gets you a vector orthogonal to this one given vector. And in 3 dimensions, you could do something similar, right? If I give you a vector that has 3 components, then there is an entire plane of directions orthogonal to it. And you could also solve, right? It might take a bit more creativity, a bit longer, but you could also solve for the infinitely many vectors that's orthogonal to one given vector. But remember, one of our primary examples, primary motivators for vectors was finding a way to describe a plane. So if I'm in 3 ambient dimensions, I want to find a way to describe what a flat 2-dimensional surface looks like, right? A plane in 3 dimensions. So here's another new operation, and this is called the cross product. Okay, so given vectors v1 with components a1, b1, c1, v2 with components a2, b2, c2, the cross product is the following. Now this comes up as it's a slightly weird formula, but here's what it is. v1 cross v2, it's called cross because it's a multiplication symbol like a cross. It's actually a vector, all right? So instead of outputting a number like before, it's a vector. It's a cross, it outputs a vector given by the following formula. Now, this is slightly hard to state directly, but schematically, here's what's happening, all right? I'm going to do a box with vertical sides here, and I'm going to do the following. I'm going to put I, J, K up on top. These are the unit vectors, right? These are vectors pointing in the X, Y, and Z directions. This is not going to make a whole lot of sense at first, but stick with me. So I'm going to put I, J, K just as symbols up top in the first row. I'm going to put A1, B1, C1 underneath. So that's the components of V1 here in the second row. And then A2, B2, C2 here in the third row. All right. And now, what does this mean? This means how I evaluate this is the output of this is going to be the following. It's going to be a vector where in the x component, I'm going to multiply b1 with b2, with c2. So I'm going to add this up. I'm going to multiply this, and then I'm going to subtract b2 times c1. So what's going on here is I'm going to do b1 times c2, and I'm going to subtract off b2 times c1. All right, so when I go this way, it's plus, this way it's minus. Now on the jth component, I'm going to help myself out here. I'm going to translate this column over here. All right, so imagine like a ghost column here. I'm going to put A1, A2 here. And for the jth jth component, I'm going to put C1, A2. Maybe I'll do red here. So this is C1 times A2, and then C2 times A1. And I'm going to do C1, A2 minus C2, A1. And then for the kth component, I'm going to do the remaining part here. Is the kth component. I'm going to look at this box, and this is going to be A1, B2 minus A2, B1. All right, so altogether, B1 cross B2 is the following as components: B1, C2 minus B2, C1, C1, A2 minus C2, A1, A1, B2 minus A2, B1. All right, so that's the output. The cross product, unlike the dot product, only works in 3 dimensions. All right, this is something specific to 3-dimensional vectors. You cannot do this procedure in any other dimension. We could maybe talk about that more next time as well.